Hello friends and welcome at my channel. Today I would like to explain to you some basic concepts of Pascal's triangle, like the very beginning, the structure of it, and well, we just prove one identity. I tried not to overload the videos, not to merge too many things, so let's keep it maybe more precise, and I hope it helps you. So, if we look at the triangle, which actually wasn't discovered by Blaise Pascal, Chinese and Indian mathematicians were using it way more before his time, but like normally Europeans tended to just name the things after their heroes and not after Chinese or India heroes. That's the story. So that's why we call it Blaise Pascal's triangle. And the idea is we start with 1, then in the next line we get 1, 1. In the third line we get 1, 2, 1. In the next line we keep 1, then we add the numbers in between. We got 3, 3, 1, and so on. So this is a pretty nice game. You can do it with kids and so on. But the thing is, later it came out that it's, well, very useful to kind of memorize this pattern, because it's also being used if we are trying to solve the parentheses for a plus b to the power of n. Why is that the case? Well, if I look at a plus b to the power of 0, I just only have 1. If I look at a plus b to the power of 1, I can write it as 1 times a plus 1 times b, which are 2 1s in both cases. If I look at a plus b squared, I'm going to have 1 times a squared plus 2 times a times b plus 1 times b squared. And now you see what's happening. We just have 1, 2, 1. And if we consider a plus b cubed, we are going to have a cubed plus 3a squared b plus 3ab squared plus b cubed, which is 1, 3, 3, 1. And now you can compare it to the lines we have in the triangle, and you see it's perfectly the case. So without even multiplying anything out, I can guarantee, you see that, 1, 4, 6, 4, 1. I can write immediately, like this is what I'm seeing right now. I do not know for sure or for 100% that it works. This is the first observation, and later on we can prove it either by induction or whatever technique you want to use. So we have a plus b to the power of 4 is going to be a to the power of 4, 1, as you can see. The next one is 4. We decrease the exponent by 1, so it's a cubed b. You see the number, the sum of the powers is always n. In this case, it's 4. Then plus 6 a squared b squared plus 4ab cubed and 1b to the power of 4. So that's the story. Okay, and one of the key concepts in this Pascal's triangle is, we can keep going forever. There are so many different properties. Like if mathematicians are meeting at Congress, normally everybody has something new about Pascal's triangle which wasn't discovered previously. In the next videos, I'll explain a bit more about Pascal's triangle as well, but today I wanted to prove one very important property. We can consider such a triangle also slightly different. Look at this. 1, we can rewrite it as we have 0 choose 0 because of 0 factorial, blah blah, what we've done. Here we have 1 choose 0 and 1 choose 1. The next line we got 2 choose 0, 2 choose 1, and 2 choose 2. And the line after is 3 choose 0, 3 choose 1, 3 choose 2, and 3, choose 3, and so on. So this is exactly the same, but what we see here, those two numbers added together are giving us the number in between. The same must be working also for the binomial coefficients, if that's the truth. Okay, and this is exactly what we would like to prove. So the statement is, as you can see, n choose k plus n choose k plus 1 is going to be one more n plus 1 and then choose k plus 1. This is the statement, and this is also called Pascal's identity. Pascal's identity. How can we prove it? Because it's so nice. It's useful also to verify it works really all the time. Well, the verification is pretty straightforward. We're taking the right-hand side and we're taking also the left-hand side, and we show that they're together. I just prove it here. So n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. All right? Yeah, that seems to be correct. And now let's start with the left-hand side. So we just consider n choose k plus n choose k plus 1. Let's rewrite the binomial coefficients. So we have n factorial divided over k factorial times n minus k factorial plus n factorial divided over k plus 1 factorial times n minus k minus 1 factorial. I hope you can follow me. I'm just subtracting k and 1 at the same time. So now let's rewrite it slightly differently. So we just keep k factorial, and n minus k factorial we're just writing as n minus k minus 1 factorial, and now we're multiplying it times 1, which we write as n minus. So we still have, sorry, my bad, still have n minus k. Was trying to skip a step. I'm not doing it. I still have n minus k. Once again, if we have 8 factorial, we can write it as 7 factorial times 8. So if I have n factorial, this is n minus 1 factorial times n. And correspondingly, if we have n minus k factorial, this is n minus k minus 1 factorial times n minus k, which I have here. Plus, we keep n factorial, k plus 1 factorial, we write it down as k factorial times k plus 1 times n minus k minus 1 factorial. That's the story. So, in the next step, what we're doing is, as you can see, we are missing on the left-hand side k plus 1 in the left fraction, and in the right fraction, we're missing n minus k. So we take the first fraction, n factorial, divided over k factorial times n minus k minus 1 factorial times n minus k. We keep it the way it was previously. We're not changing anything. And we're multiplying it now times 1, now this is the case, which we write down as k plus 1 divided by k plus 1. I'm not changing anything. Plus n factorial divided over k factorial times k plus 1 times n minus k minus 1 factorial. Everything is the same, but now we also multiply times 1, which we rewrite as n minus k divided by n minus k, because this will bring us to n minus k factorial. Now we have two equal denominators, as you can see. So we have to multiply n factorial times k plus 1, and then we add n factorial times n minus k divided over. Here we can put k factorial and k plus 1 to k plus 1 factorial, and minus k, n minus k minus 1 factorial times n minus k to n minus k factorial. Now let's take n factorial in the numerator outside of the parentheses. We would have k plus 1 plus n minus k divided over k plus 1 factorial times n minus k factorial. You see k's are canceling, and we have n factorial times n plus 1 divided over k plus 1 factorial times n minus k factorial. In the next step, we recognize that n factorial times n plus 1 is just n plus 1 factorial in the numerator. I still keep k plus 1 factorial in here, and this fraction, these parentheses are going to be slightly changed. I'm just writing n plus 1 minus k plus 1 factorial. Look at this. I haven't changed anything. I just added 1 and subtracted it at the same time. So it's still addition of 0. And now if you look at this, this is n plus 1, choose k plus 1 through the definition of n choose k. So this is n plus 1, choose k plus 1. And we're done with the proof. Okay, so this is the key equation, key identity for the whole computations on Pascal's triangle. And we are going to, well, go a bit deeper into the properties of Pascal's triangle, but I think it's a good start. So it's enough for today. Thanks for watching, and yeah, enjoy more math on my channel. Thank you, guys.